Traditional shape and reflectance estimation technique rely on direct photons or single bounce light paths. In this paper, we present a framework for shape and reflectance estimation from indirect photons. Our world is filled with complex scene-light interactions for which the single bounce light path assumption does not hold. Can multi-bounce light paths be used to infer the shape and reflectance of a scene? In this work, we study two-bounce light paths, the simplest version of multi-bounce light paths. There are several reasons why we want to consider two-bounce light paths. First, the number of available light paths is larger. For example, for a scene with 1,000 patches, there are at most 1,000 one-bounce light paths. There can be 1 million two-bounce light paths. This over-constrains the problem of shape estimation and can potentially lead to more robust shape estimation techniques. Second, for many specular scenes, we often cannot observe any single bounce light paths. This is particularly true when there are specular objects in the scene. With two bounce light paths, this is less likely to be a problem. Finally, two bounce light paths sample the reflectance functions of the scene with a greater angular spread. As shown in the plots above that capture the spread of angular sampling in a bivariate representation, two bounce light paths have a greater coverage than single bounce light paths. There are two kinds of information that we can obtain for a two bounce light path. One, the time of flight information, which gives us the total path length taken by light. Second, light transport, which is the fraction of light that can be observed by the camera after the two bounces. These two pieces of information are particularly useful, since it gives constraints on the shape and reflectance of the scene. If we consider a collocated system, a two-bounce light path will form a triangle. Given the perimeter of the triangle, can we find the depth? The answer is no. If we increase the length on the left edge of the triangle, shortening the right edge will give us the same time of flight. Therefore, we need to use multiple measurements to simultaneously estimate the depth. To efficiently encode the available information of two bounce light paths, we construct a light path graph, where each node represents a scene point and each edge represents whether the two bounce light path can be measured. Once the light path graph is constructed, we can study its topology to see if the information is adequate for shape recovery. A key result of our work is to show that the shape of the object can be uniquely recovered provided the light path graph contains two cycles. This also tells us that the uniqueness of shape recovery is solely dependent on the topology of the light path graph. Here we show our shape recovery results using two bounce light paths. Once the shape of the object is obtained, reflectance estimation becomes feasible. The observed light transport L is essentially the product of a geometric term. One BRDF sample at first bounce, another geometric term, another BRDF sample at second bounce, and another geometric term. Since the shape is known, we can account for the geometric term. Thus, the two BRDF terms are only unknowns. By using the Ashok-Shirley BRDF parametric model and assuming that the scene contains one material, we can recover reflectance from two bounce light paths. For more details, visit our lab webpage.